Hello, everyone. I'm Warda Ashraf. I'm an assistant professor at the University of Texas at Arlington. Today, I'm going to talk about how we can modify certain properties of CSH using biomimetic molecules. This work is actually done by my PhD students, Intezarul Haq and Ishad Baki Borno. They did everything. I'm just taking the credits here. That's what assistant professors do, right? Okay, so welcome to my presentation. So first, what is calcium silicate hydrate? Calcium silicate hydrate is the primary binding phase of Portland cement-based materials. For most of the macroscopic properties that we see is strength, durability, those are coming from this CSH. So what I have here is a schematic presenting a very simplified molecular structure of CSH. So essentially, we have the silicate tetrahedral units. It forms like a layer. So it's a chain-like a structure. Okay, so it's a, oops. Okay. No, that's fine. I think it will be good. So this silica structure, it forms like a layer type of a structure, so chain-like a structure. And in between the layers, we have calcium ions. Now, when we are saying that we are modifying the properties, in this work, we are primarily interested to improve the carbonation resistance of CSH. What is carbonation? So CSH, in the presence of moisture, it will react with carbon dioxide and it will form silica gel and calcium carbonate. It's a decalcification process. So essentially, we are extracting the calcium and we are forming calcium carbonate and silica gel. Silica gel is a highly polymerized network of these silicate tetrahedral units. So what happens is that during this conversion of CSH to silica gel, there will be a reduction in volume. Due to that reduction in volume, we will see increased porosity and also increase in the critical pore size. In addition to that, we can also see carbonation-induced corrosion. That is mainly because of the reduction in pH. This process is unavoidable because in our atmosphere, we have around 0.04% of CO2. This carbonation-induced degradation of CSH, it is primarily a problem for certain sustainable binders, including calcium-rich alkali activated material and concrete prepared with high volume of supplementary cementitious materials. That's because these materials, they do not contain calcium hydroxide. They mainly produce calcium silicate hydrate. So the degradation of CSH is a major problem for them. So our goal is to prevent that degradation of CSH, and we would like to do that by controlling the crystallization of calcium carbonate. Okay, so let's see more about calcium carbonate. So calcium carbonate is one of the reaction product of that carbonation. It can have different polymorphs. We have aragonite, vaterite, amorphous calcium carbonate, and calcite. Among these, calcite is the most thermodynamically stable one. So what happens is that during carbonation, even if you see some vaterite or amorphous calcium carbonate is just metastable phase, eventually it will convert to calcite. All of these phases, they have different solubility, they have different hardness, and they have different density. Previous studies have shown that instead of calcite, which is the stable phase, instead of calcite, if we could stabilize vaterite and amorphous calcium carbonate, it will help us to reduce the carbonation degradation. Because these two phases, they have higher solubility and also they have low density. That means formation of these phases will give us pore size refinement. So that's our goal. We want to stabilize vaterite and ACC formation during the CSH carbonation. But how do we control calcium carbonate crystallization? In our cement area or cement-based industry, there is not a lot of work on how to control this calcium carbonate crystallization, but we can learn from the biomineralization process, natural materials. So what happens in this, in such materials such as nacre or mother of pearl, we have learned that these living organisms, it can control the calcium carbonate crystallization using certain organic molecules. And by this process, it actually forms organic inorganic hybrid phase with superior mechanical performance. As an example, if you see this figure on the right side, if you have pure calcite crystal, your modulus is around 2 to 2.5 gigapascal. But if you modify the crystallization using those organic additives, you can increase the hardness up to 4 gigapascal. So it's like almost double. So essentially, we are going to adopt this technology, but in case of our CSH carbonation degradation, right? So we are going to use certain molecules which will help us to mimic this biomineralization process. And that's why we are addressing those as biomimetic molecules. This schematic is kind of simplifying our technique, what is happening with and without the molecules. If we do not have the biomimetic molecules, what happens is that we have a source of calcium. It will react with carbon dioxide in the presence of water. First reaction product to precipitate is always amorphous calcium carbonate, but that is metastable. So amorphous calcium carbonate will eventually convert to calcite. This is a very well-known Oswald process. Our least stable phase will precipitate first, eventually it will convert. If we have biomimetic molecules, what happens? Again, our first product is going to be amorphous calcium carbonate. However, these biomimetic molecules, it will be actually absorbed on the surface of ACC. And because of the surface absorption, it will prevent further conversion to more stable phases. So this amorphous calcium carbonate, it will remain as amorphous calcium carbonate, and it will form bond with those organic molecules, so eventually forming those organic inorganic hybrid phase, which we are expecting that it will provide us better mechanical performance. Whether it will stabilize ACC or vatorite, that depends on what type of molecule we are going to use. So here is our simplified research goal. We will use certain biomimetic molecules to modify our CSH and to improve its resistance to carbonation. This is a purely experimental work. So these are the molecules we are going to use. We have used L-Aspartic acid and polydopamine. Based on our previous work, we learned that L-Aspartic acid helps us to stabilize amorphous calcium carbonate, whereas polydopamine, it helps us to stabilize vatorite. Okay, so they focus on different polymorph of calcium carbonate. We did direct synthesis of CSH with a target ratio of calcium to silica 1.5. We followed same steps as you would to produce polymer modified CSH. The method is kind of well known. Eventually, our product is powder CSH. We compress it to prepare tiny pellets, and then we expose that pellet to carbon dioxide environment that contains like around 4% CO2. Findings. So let's see what happens if we modify those CSH using biomimetic molecules. So the first one is just these plots are just to show the characteristics of our synthesized CSH. The first one is the XRD. The takeaway point from here is that CSH synthesis usually is very difficult. It gets carbonated. We are only showing that the carbonation was, even though we are doing it in the glove box, the carbonation was minimal. We had 90% pure CSH. In case of XRF, we saw that even though our target calcium to silica ratio was around 1.5, we ended up getting around 1. That is expected because this synthesis reaction is not 100% efficient. So we will have some loss there. So the actual ratio is 1. So these are just some TM, transmission electron microscopic images showing what happens to the CSH after the molecule modification. So this is the control batch. Amorphous phase, it's just lath-like deposition. You cannot see any specific structure there. So it's just control CSH. After this biomimetic molecule modification, what we saw is that there were more foil-like deposition of CSH. We could also see from the images that it appeared to become more denser. So that's how the molecule modified the morphology of CSH. Next, we'll look into the 29 silica NMR spectra, nuclear magnetic resonance spectra. It helps us to understand how those silica tetrahedra that I was talking about, how those are connected. So understanding the CSH structure. This is before carbonation. So what happens is that control CSH, because our calcium to silica ratio was 1, we have Q1 and Q2 species, but higher intensity for Q2 species. It simply confirms that we have that layer-like CSH structure. In case of our polymer modified one, we have very similar polymerization. So we can confidently say that this polymer addition actually did not significantly affect the linear structure of CSH. So this is before carbonation. Then we expose it to carbonation for 168 hours at 4% CO2 environment. What happens in case of control CSH, we see the formation of Q3 and Q4 species. Q3 and Q4 actually indicates that the formation of highly polymerized silica tetrahedra. So this simply confirms that after 168 hours of carbonation, this CSH fully converted to highly polymerized silica gel. On the other hand, this molecular modified one, even after 168 hours of carbonation, it was able to retain its original chain-like structure. So we can still see the Q1 and Q2 species. We continued the carbonation for 28 days. Control batch, the CSH already, it's fully damaged. We see only the formation of Q3 and Q4. So nothing is happening there, it's already damaged. In case of our L-Aspartic and polydopamine modified one, after 28 days, we can see some shoulder of the polymerized silica gel formation. So some of the Q3 and Q4 species. But still the highest intensity was for both Q1 and Q2. So we say that we still have the original CSH structure. So essentially our takeaway point from this slide is that both of our biomimetic molecules, L-Aspartic and polydopamine, it was able to improve the resistance of CSH to carbonation. L-Aspartic acid was more effective comparing the Q3 shoulder intensity here. Our main hypothesis was we can control the calcium carbonate crystallization. We can control what type of polymorph is forming. So to monitor the calcium carbonate polymorph, one of the very well-known technique is the infrared spectroscopy. It helps us to identify what we are forming. Essentially, we look at around 1400 wave number here. If we have a very sharp peak, that indicates calcite. If we have a split peak or tabletop peak, that indicates we have either amorphous calcium carbonate or vaterite formation. In case of control batch, we saw that initially we had some vaterite and amorphous calcium carbonate formation, but after 28 days, calcite is the most prominent form of calcium carbonate in that system. This one is L-Aspartic containing CSH, and essentially what we saw here is that even after 28 days, we have a stable form of amorphous calcium carbonate and vaterite in the system. We also looked into the silica gel polymerization here again by looking at 900 to 1200 wavelength. That helps us to understand how the silicate is polymerizing. So we took the mean wave number of this range and plotted here. So what we see here, this blue and red, these are the molecule modified ones. So for CSH, the mean wave number is usually from 960 to 1000. So what we learned from here is that up to 28 days, our molecular modified ones, it was able to retain the CSH structure. The wave number is very similar to our initial batch, even though it was slightly increasing. In case of control batch, the damage starts happening after 24 hours, and after 168 hours, it was like fully damaged. So after that, there wasn't any CSH in that system. TM images, so from the control batch, we could identify the formation of silica gel, as you can see here, almost like a spherical deposition with denser periphery. In case of our polydopamine and L-Aspartic batch, there wasn't any change because again, the degradation didn't happen. Finally, we also looked into the nanomechanical properties. So essentially, we have compressed pellet and we use that for nanoindentation. Here are the experimental setups. So we did almost 120 nanoindentation and plotted the frequency distribution. So this is before carbonation. In case of control batch, it has an elastic modulus of around 3 gigapascal. It matches well with the previously reported data. This is pure CSH. In case of polydopamine modified one, the average was around 30 gigapascal, and L-Aspartic modified one, it had the average of around 9 gigapascal. So even without the carbonation, this biomimetic molecule can increase the elastic modulus of CSH from like somewhere from 3 times to 10 times. After carbonation, something interesting happens. So in case of control batch, the average was around 3 gigapascal. That increases to around 10 or 11 gigapascal. That's simply because calcite has higher modulus, so the average increased a little bit. But the shift was higher in case of this biomimetic molecule modified one, especially if you look at the L-Aspartic modified batch, it was initially 9 gigapascal. After 168 hours of carbonation, the average became 55 gigapascal. Let me also remind you here that pure calcite crystal, it can have elastic modulus of around 60 to 70 gigapascal. But for those batches, we are getting modulus up to 100 gigapascal, so significantly increased. Also, in case of L-Aspartic batch, what we have seen that for that batch, the carbonation extent was the lowest, but the modulus increase is highest for this batch. So essentially, we are saying that for this batch, even though there is a small amount of carbonation, it essentially formed those organic-inorganic hybrid phase, which are known to provide higher elastic modulus. And so our takeaway point from this slide is that if you do this biomimetic molecule modification, it increases the elastic modulus of CSH both before and after carbonation. After carbonation, the change is much more prominent. So CO2 sequestration, so all of us, we are kind of interested in how much CO2 we are sequestering in the system, but once you start playing with the polymorph of calcium carbonate, we cannot use anymore the simple thermogravimetric analysis because different polymorph of calcium carbonate decompose at different temperature. So we are using thermogravimetric analysis with mass spectra, and this is the CO2 mass spectra. So from this, we can determine how much CO2 we are sequestering in the system. What we learned is that control batch had higher CO2 sequestration, around 20%. Molecule modified was like 10 to 15%, obviously, because we are trying to reduce the extent of carbonation. But it was interesting to notice is that this modification, even though, so it was able to retain the original CSH structure and at the same time was able to give some CO2 sequestration. So we are sequestering CO2 without damaging our original CSH phase. Finally, we have the calcium carbonate morphology because that's what we are talking about, right? So calcite has rhombohedral crystals, so you are supposed to see sharp edges. So in the control batch, we could see those sharp edges here and some here. Most of these calcite crystals are embedded in silica gel. In case of our L-Aspartic and polydopamine modified batches, we could see that the sharp edges become more rounder. So this is what happens when you are converting calcite to either vaterite or amorphous calcium carbonate. You are stabilizing those phases. We could also see that the calcium carbonate crystals, they are bonding with each other with another phase in between. So this is essentially what we are suggesting is our organic-inorganic hybrid phase. So I believe that's all the experimental data. So concluding point is that we can do biomimetic molecule modification, and this helps us to improve the elastic properties of CSH. It also helps us to improve the resistance of CSH to certain durability damages. We experimented with carbonation, but we might do some other experimental condition in the future. What is the final application of this type of work? So we are expecting that these biomimetic molecules, once we select their dosage and what type of molecules we are using, it can be used as chemical admixture for sustainable binders, including alkali activated materials or concrete with high volume of SCM. Selection and screening of these molecules is very challenging. We're still working on it, and we have so many failure experiments. But that's all I have for you today. Thank you very much for your attention. If you have any question, I'll be happy to answer. Thank you.